In the previous sections, we've implemented the core UTXO logic. At this point, we've written a lot of code. So before doing more, let's learn how to write some tests in Substrate. In this short section, I'll show you how to construct a blockchain testing environment, build some initial state prior to each test, as well as also show you the helper functions that are available to you for testing. Let's go ahead and switch into the tests module in utxo.rs and start constructing our testing environment. Scrolling down to the test module, you can see that by default, a lot has already been scaffolded for you here. Starting at the top, we're importing some dependencies. This uSuper actually refers to the UTXO module above. So we're using what we've implemented so far, like a library. We also use some custom traits that will come in handy for constructing variables in testing. The following snippets here construct a test object, which contains your runtime construction in the test environment. We implement the same necessary traits here that we inherited above, if you recall, in our UTXO implementation. And we satisfy the traits type definitions requirements with a lot of defaults and nil values, since we're only really testing the scope of this UTXO module and not much other full blockchain functionality. So you don't have to worry too much about what all of these type definitions mean. And down here, we simply alias this test object, which we created up here, which now works as a type specifier for this entire test module. This definition allows us to later easily invoke everything that we inherited above, including our UTXO functions and storage access. Okay, so first we need to build our testing mockup. This mockup will build the initial chain storage for each of our unit tests that we're going to write. We're going to need something from Substrate called testing externalities. Flipping back to the Substrate reference documentation, according to the documentation, externalities just provide access to storage and to registered extensions. And extensions are, for example, the key store, which we'll talk about shortly. So it looks like this will come in handy as we construct our testing mockup. Let's use it by declaring a function. Let's call this function new test ext. And this function, each new test will invoke, which will give us back test externalities from the SPIO crate. And inside, let's construct externalities the efficient way by using what we're already inheriting, i.e. systems Genesis configuration defaults. Let mut t, getting the Genesis configurations defaults, and using that to build the initial storage for this test object, before finally unwrapping the storage value inside. At this moment, t is still a type of storage variable. So next, let's get our actual externality. By invoking test externalities and converting the storage t into the actual externality that we're looking for, before finally returning this function variable. At this point, let's scroll up to declare storage. And if you recall that previously here, when we created UTXO store, we extended the functionality to be able to pass in a vector of transaction outputs and designate that as the Genesis UTXOs. So conveniently, we can make use of this to construct initial testing parameters. So let's make use of it in constructing our test externalities. We need to do three things. Namely, the first is we'll need to create keys for a test user, say Alice, who will own the UTXOs in the first place. Secondly, we'll need to store a seed UTXO, say UTXO containing a value of 100, that's owned by Alice, in our Genesis storage, using the build closure that we implemented above. And lastly, we want to store Alice's keys in storage as well, so that her public keys are later retrievable by our individual unit tests, as we'll need to do things like signature verifications later on. With that in mind, let's go ahead and implement this. To construct a new public-private key pair for Alice, we'll need to do let key store to get a new key store variable. It turns out in testing, we can create a new key storage to store new key pairs. Next, let's construct a public-private key pair for Alice, and the variable that we'll get back from the function we'll use is just Alice's public key. And we want to, in one fell swoop, also write her key sets to the key store. So let's go ahead and do key store write. And what are we writing in there? Well, let's generate using the SR25519 signature scheme. Generate new keys. And what this function is going to expect is first the key type ID, which in this case is going to be still SR25519. And then in the next parameter, it's going to expect an option containing some seed phrase from which it will generate the key pairs. So let's pass in some containing a static variable Alice phrase, which we'll construct shortly. And don't forget to unwrap the variable inside so that we can get Alice's public key back. Okay, let's go ahead and create a global constant, i.e. the 12-word mnemonic called Alice phrase. Constant Alice phrase, which is going to be a static string. And I'm just going to paste in here something that I've already generated. You can use the same mnemonic phrase as me, or find any online mnemonic generator and get your own custom phrase. Next, let's take our storage variable that we constructed from system Genesis configuration defaults, and we want to extend that by passing in our vector of Genesis UTXOs. So let's do t.top, which retrieves the relevant parts of storage that we want to be appending information to. And let's go ahead and extend that. We'll be extending it with a Genesis config struct for our UTXO module, which, like we declared above, will be expecting a configuration variable named Genesis UTXOs, which, as we designed, will be expecting a vector containing some transaction outputs. At this point, in case Genesis config is expecting some more variables, a very easy way to get around that is with the special Rust syntax, default, which simply populates all of the other expected parameters with its default values. So we can focus on just constructing what's custom. Okay, so let's go ahead and build this default seed UTXO of value 100 owned by Alice that we want to exist upon block number 0. So let's create a transaction output of value 100 with Alice's pub key in type H256. At this point, we're ready to build the storage. Unwrapping the value that's returned, and accessing just the top part of the state storage tree. And last but not least, we'll still need to store Alice's keys into storage. So let's go ahead and do that with one simple line. Let's take our externality, and simply we just want to register this extension, namely a key store extension constructed from this key store that we just created. And that's it. We now have our test extensions that each of our future unit tests will be able to build on top of. Next, I'll show you how to write a unit test in Substrate. Underneath your new test extension function, all Rust tests are preceded with a test attribute, namely #test. Let's create a simple test called test simple transaction to test whether or not our spend function and all of our writes to state work. To use the test externality that we just created above, let's invoke it here and use execute with, whose closure will contain the bulk of our testing logic. This is how the test setup in almost all Substrate tests will look. Great. Inside, let's first retrieve Alice's public key. So let Alice pub key from the SPIO crypto crate. We can actually retrieve the public keys that we previously wrote to the key store by using the function sr25519 public keys, giving it the same key ID that we created the keys with. And this will return a vector. And since we only created one key, we'll get the key at index 0. Okay, so in this simple test, let's have Alice send herself a new UTXO of value 50. And let's have her burn the remainder of that value. So let's go ahead and create a mutable transaction called transaction, which is going to be a transaction struct with an input of a vector containing a transaction input with an out point that's h256 from a static variable that I'm going to create called Genesis UTXO. Recall that this needs to be the storage hash of the transaction output that we created here. Now offline, I've previously written a print line here and manually calculated what this hash needs to be. So I'll go ahead and copy over the hard-coded hash here. And to derive a hex from string, you're going to need to manually import this crate, since it's not included here for you by default. I'll leave it as an open exercise for you to derive that the storage hash of our Genesis UTXO is indeed this hexadecimal string here. Next, let's populate the SIG script. Recall that if Alice were to submit this transaction, first she needs to sign over this entire transaction with the SIG script as all zeros. Next, let's create an outputs vector containing a transaction output of value 50. And Alice is sending this to herself, so the pub key designation will just be Alice's pub key again. Let's now have Alice sign over this transaction that she wants to execute. So let Alice signature. And the function we can use here is sr25519 sign from the SPIO crypto crate, passing in SR25519 as the key ID. Next, this function expects the public pair of the private key that it will actually use to sign a particular message. In this case, it will be Alice's public key. And finally, it's going to expect the message that it will sign over with Alice's private key. In this case, let's give it a reference to the encoding of the transaction. Before unwrapping the final return value, which will be Alice's finished signature. We're now ready to inject the SIG script back into Alice's transaction. By doing transaction inputs, reaching into the first input, and modifying the SIG script. And don't forget to do a type conversion, turning Alice signature, which is of type signature, into a H512 hash. And finally, let's calculate the new UTXO hash for Alice's new UTXO of value 50, which will be a Blake2 256 hash of the following tuple, containing the transaction encoding, as well as the index of this particular transaction, which in this case, since it's the only output, will be 0, passing it in as an unsigned integer of 64 bits. Okay, so let's go ahead and invoke the spend function, passing in this transaction. We're going to expect that the spend transaction, and recall that it returns a dispatch result type, that the spend transaction is going to execute smoothly, returning an OK. In Substrate, you get access to a special test function called assertOK to do this. So let's invoke our spend function. And if you recall, our spend function expects a first parameter of type origin. You don't really need to worry about what that means for now, so you can just type what I've typed here, passing in the second variable, which is the transaction itself. Okay, at this point, we're ready to make some actual testing assertions. So first, we'll expect that when we spend this transaction on behalf of Alice, that everything will be okay. Recall that the spend function returns a dispatch result type, and so in this case, we want to make sure that that is the result we're getting. Secondly, we should expect that the old UTXO that Alice has spent will disappear. And last but not least, we should expect that the new UTXO will exist. And not only that, it will also have a value of 50. So in the Substrate macro frame support, there is an expression called assertOK, which will execute the expression inside and make sure that the return value is of type OK. So let's do UTXO spend and invoke the spend function, passing in the transaction. Recall that our spend function also took in a parameter of type origin. For the scope of this tutorial, we don't have to worry about what that is, so you can place in the default expression I've written for you here. Next, we want to assert that the old UTXO is gone. So to assert a Boolean value, we can call another macro that's just called assert, and we want to assert the opposite of the fact that UTXO store contains the old UTXO key. And recall that the hash of the old UTXO was Genesis UTXO. And finally, let's go ahead and assert that this new UTXO does indeed exist in our UTXO store. by passing in the new UTXO hash. And not only that, we now want to assert an equivalence that this new UTXO value is indeed 50. Let's flip back to our terminal. And inside the root directory, to run this test, you're going to want to do cargo test, referencing the particular package that we're building, which is called UTXO runtime, to execute your test. And this might take a couple of minutes. It looks like I've made a couple of spelling errors, so let me just go in and fix that. This should be SR25519. And let me fix the typo here. And we see that our test has successfully executed with one test passing, namely our test simple transaction.